Good day, grade 12 learners. Welcome to today's Technical Science Paper 1 lesson. My name is Jabu Sithole. This lesson is brought to you by Gauteng Department of Education in collaboration with Sibona Discovery Center and broadcast by Phakama Research and Development. Today's lesson is a continuation of last week lessons where we spoke about momentum, change in momentum, and impulse. However, today we'll be dealing with the topic says principle of conservation of linear momentum. That is going to be our lesson for today. But we need to recap as to what have we've learned about momentum. Remember, the topic that we're dealing, it's a continuation, it's centered around this word, momentum. We said momentum is a product of mass and velocity, a product. What did we say? We said it equals to m multiplied by v. It's a product of mass and velocity. That is momentum. I'm just recapping what we have done. And we went as far as change in momentum. And we said change in momentum is a difference between final velocity and initial velocity. That is a change in momentum. And we came with a formula that will help us to calculate the change in momentum. And the formula is delta P equals to final momentum minus initial momentum. Then we came with this formula that we said we are going to use. Remember the formula, you'll get it in a data sheet. And copy the formula as it is in the data sheet. Please, learners, please copy the formula as it is. Don't design your own formula because you'll get it wrong. So this is what we said about the change in momentum. And we made some more calculations of change in momentum, of how to calculate a change in momentum. So we have tried to make calculations and we apply the formula for change in momentum. We have applied the formula for the momentum as well. So these are I'm just recapping of what we have done last week. So we came to impulse. Remember, we have to define these terms, and then we come to an understanding of an impulse. Impulse, you said, it's a network applied on an object, and the time has in contact to the object. So that this is an impulse. A net force, not a network, sorry, a net force applied on an object and the time in contact with an object. So this, we call it impulse. This side is impulse. And we said impulse, it equals to change in momentum. This is change in momentum. We know this formula, it can come here. Now, we don't define impulse as a change in momentum. That is wrong. That is the theorem, right? It's momentum theorem. If you're saying that we are not defining, but we define impulse, we've defined it. I've gave you the terminology. We'll look at the terminology again, but I'll give you the terminology for how to define impulse. Then impulse is a net force of an object in time in contact with an object. That is and impulse. Then a change in momentum, we said it's the difference between the final momentum and the initial momentum. That is the change in momentum. Now, today we are going to look to the conservation of momentum. That is what we are going to look into. We're going to zoom into it, and we're going to do a lot of calculations, because this is where your marks are, and this is where you need to practice so that you get a lot of marks. Conservation of momentum. You need to define what is conservation of momentum, or state the law of conservation of momentum, because it has a law. Then it's going to, that is 2 marks or 0. So stating or defining is 2 marks or 0. Then we need to apply the law of conservation of momentum. Law will apply it in a sense that we'll do calculations, because it's going to give us the formula that we are going to use to calculate the law of principle conservation of momentum. In fact, we call it principle of conservation of momentum or law, but let us refer to as principle. But that will be easy. The principle of conservation of momentum. So we are going to stick to this. Then this law is split into 2 collisions. In fact, it's 3 collisions, because we've got the elastic collision, we've got the inelastic collision, we've got the explosion. So we'll look at on those 3 collisions, what do they entail and how to apply them in terms of calculations. So we'll be talking about the inelastic collision, we talk about the elastic collision, and we'll talk about the explosion if time's allowed. But I'm giving you a scanty, and I'm giving you the sketch, because it is very important to know from the beginning what is it that you are going to look at. What is it that we are going to come across as we are moving along with our lesson. So this is a sketch. This I've just taken through what we did last week. Now I'm going to just move to what we are going to do this week, but I'm still going to take you through to a bit of revision, reminding you, right? Now, these are the terms and definitions for momentum that you need to know. Remember, we're talking about the external force. Then this is an external force. This is a definition for an external force. A force that can change the total mechanical energy of an object. An external force, a force, an external force is caused by an external agent from outside a system. So this is an external force. It is caused by the external, right, agency of a force that is acting on an object. So that is an external force. In other words, it's a force that is acting external. All right. Then we've got the impulse. I've defined the impulse for you. We had a definition of an impulse, so we know what is impulse. So for you to be able to define an impulse, go to the formula, look what the formula says, and then speak to the formula. Then it will give you the definition of impulse. You don't have to cram it. So we've got the impulse theory or impulse theorem. Then is what I said, is that impulse is equals to change in momentum. That is an impulse momentum theorem. So as easy as that. Then the internal force. Remember, we spoke about the external. Now we are talking about the internal force. Now the internal force, a force that cannot change the total mechanical energy of an object. Remember, the other one changes. This one cannot change, right? The internal force are forces exchanged by object within the system. Within, internal means within, external means out. In other words, the other one is acting outside, the other one is working inside of an object. So that is the difference between the two. So if you want to remember this, you will call the words external, internal, X outside, inside. So that is how we are going to recognize how to differentiate between the two forces. Then we have the term isolated system, because we are going to use the isolated system. a system in which the net external force act on the system is zero. So the external force there acting on the system, all right, is zero. That we call it an isolated system. Then we know the definition for momentum. We said is a product of mass and velocity. And then the linear momentum. Linear means straight, all right? Linear momentum is a vector quantity which with the same direction as the velocity of an object. So that is a definition. However, if we're talking about linear, we're talking about a straight line and a motion in a straight line. All right. We defined the Newton second law in terms of momentum. Then it gives us this formula that explains, in fact, the use of impulse. Remember, we talk about the use in terms of impulse in a real life situation, whereby we talk about the airbags. We talk about the cramp zones, and then the seat belts. All those, they apply in this law. Now, the law of conservation of linear momentum, that is where we are going to deal with today. The total linear momentum in an isolated system remain constant in both magnitude and direction. This is the law that we need to know. This is the law that you must know how to state it. The total, the way you see the way total is in capital letter is there. The total linear momentum in an isolated system. We have this isolated, we don't exclude the weight. It must be put there, and we have defined what is an isolated system. Remains constant in both magnitude and direction. Remains constant in both magnitude and direction. This is, so to speak, the sum of momentum is before is equals to the sum of momentum after. This is what you're going to give. This is what we're going to do. So that it tells you about the conservation, the principle of conservation of the linear momentum. Then we have elastic and inelastic collisions. Elastic collision is a collision in which both total momentum and kinetic energy are conserved. That is very important. Both, in this case, in an elastic, if we talk about elastic, both total energy, momentum and total kinetic energy are conserved. This is very important, learners. This is what you should know, because this, they may ask, define elastic collision. So in elastic, there are two things that are conserved. It's a total momentum and the total kinetic energy. Both are conserved. Then you can get this question even in your multiple choice questions, because they like this kind of question in multiple choice questions. So you can get, they say, elastic collision is, then they give you those destructors and the correct answer. So you must know that if we talk about the collision here, the elastic, there are two things that are conserved. It's total momentum and the total kinetic energy. Then inelastic, we said elastic, inelastic, here is during which the total momentum is conserved, but the total kinetic energy is not. So here, only one is conserved. It's a total momentum that is conserved, but kinetic energy is not. So elastic, two are conserved. Inelastic, one is conserved. Right. So this we should know, and this will guide us. Learners, these definitions are very important. They want you to define it, or you can get them in your multiple choice questions. Remember, your multiple choice questions, you've got 10 multiple choice questions, which are out of 20, all right, in paper 1. So you can get 20 out of 20 if you know how to play with your definitions, because they will be there in your multiple choice question, not in terms of defining it, but in terms of giving you those things, then give an answer, because you only choose. So we don't play the choosing game, but we work things out and we work it through the knowledge that we have. So these are the definitions that we need to know under the topic momentum. So let us have this, paste it in your book, look at it all the time. Let this be your Bible once you come to momentum. As you study for your examination, look at these things, and then you familiarize. What are the law? What are the definitions that I need to know? What are the principles that I need to know? Then you familiarize with these terms and definitions. So paste it in your book and then go through them. Now, conservation of linear momentum. These sections we are going to study, 1, the motion or the movement. If we talk about motion, we talk about the movement of an object in a straight line. That is linear, right? Linear is a straight line. So in a straight line momentum, that is what we are going to deal with. We are not dealing with any angles or what, but the motion in a straight line, which is linear. Then the difference between the collisions, right? Maximum of 2 objects, not more than 2. We're going to talk about 2 objects that they are colliding here. So the maximum of 2 objects. So in this one, the collision that we look at, well, is going to be at 2 objects when colliding. That is very important. Now, namely, one moving object collides with a stationary object. Stationary, that is rest. Other words, if we look at before, right, we have, let us assume, but we not assume, is what is it? The car, the small car here is just standing because it has the velocity of 0 meters per second. So it is not in motion, it's not moving. So it's stationary. So here comes a big truck behind, moving at the velocity of 10 meters per second. Then it collides with this one that is stationary. So I'm talking about 2 objects, right? Before, right? The same object after collision, because they collide here, there will be a collision. Now, the same object after collision, what happened? The stationary object moved forward with what? The velocity of 15 meters per second, right? It means the other one hit the stationary car and the stationary car moved forward. So what happened with the car that collides with the stationary car? It means we will be calculating the velocity because we will be not knowing the velocity of that car. So we need to calculate the velocity. Remember, velocity is a vector. It must have both direction and quantity, right? So, a magnitude. So it must have a magnitude and the direction. So we will be knowing the direction of the car, whether when immediately it hit the stationary car, it went back or it moved forward. So the velocity will tell us, right? Because it has what? A direction. It is a vector. All right. So here we're looking at one object is stationary, or it's at rest, does not moving, or is not moving. It's just standing there. Then number 2, we look at this calculation of the linear. They look at the object moving towards each other and collide. So in other words, these objects, they are approaching one another, one from west or east and the other one west. Now they collide each other. After collision, they get back where they come from. So they repel or they bounce off, right, to each other. In other words, these are the two objects approaching one another. We've got this object is, which is M1, this is M2. Then they're approaching one another. Somewhere here they collide. All right. After collision, they went back where they come from. This one, this way, this one, this way. So in other words, this one they bounce back. All right. So this is another type of collision, but as we're still maintaining, we're using only two objects. All right. Now we've got the third one, which is the explosion. As I mentioned that we've got an explosion. Now this one, we can say this is a bit of a bomb. So we've got a bomb. It's solid, right? Before it's solid, right? It means it's in one, right? Then after collision or after you have exploded, then it gets into pieces. This is an explosion. But we'll have calculations if need be for how the explosion is being calculated. Right. Now, the fourth one, with the object moving in the same direction and they collide. They are moving in the same direction following one another as the one that we did before, moving in the same, but now they collide here. After collision, they move in the same direction as well, right? They follow one another after collision, but they don't join together. They just bounce back, but following one another. That is what is happening. It's a fourth one. Then the fifth one is when an object moving in the same direction as they collide. Yes, they are moving in the same direction as they collide, but they cling together after collision. These ones, they are separated. They are moving in the same direction. They collide somewhere. After collision, they cling together. They move off. We will see the weights. The weight will be clinging together, move off together, right? The other ones, the way that you must look at it, bounce back. So once it bounces back, then it tells you about something. So these are the kinds of linear momentum that we have. There are 5 of them. You must know them. Then I've given you a glimpse of them. Now, to better understand the above collision, you should familiarize yourself with the following concept. We spoke about them in our definition. We spoke about the system. What is a system? It's when a number of objects and their interaction with each other. It's a known number of objects. It's a known number of objects and their interaction with each other. So this is a system. So a system is a known number of objects, right? And they are interacting to each other. So there is an interaction between those objects, but they are in one common place. Isolated system, this is very important, or a closed system. You will be asked, what is an isolated system? Or what is a closed system? As we've mentioned the other way, is a system in which no external forces act. System as to no external forces act. That is an isolated system. Then we talk about the external forces. I've given you definition for external forces. Forces outside, acting outside the system. That is an external force. E.g., we have friction, we have got applied force. Those are the forces that are acting externally. We've got conservation of momentum. The term conservation, remain constant. This is the term we said we conserve. If we conserve something, you remain constant or you remain the same. So that is conserve. You're conserving something. There's a way that we are conservative. So it means it doesn't change. You remain the same. Then elastic, I've mentioned the elastic. Then I've defined them. You must know this elastic. I said there are 2 things that you need to know in elastic collision. is that total momentum and total kinetic energy are conserved. The other one's only one that is conserved is total momentum. That is conserved, but not the kinetic. So these are the terms that you must familiarize yourself with. Now, the principle. Remember, I was not talking about the principle. Here I was explaining just what is linear. The conservation of linear momentum. So I was telling you about the term. I was telling you about how you do identify the conservation of linear momentum. It's what I said. But now we are going to the principle of it. What is the principle? The principle states that this is what I'm going to write here. NB. You must know. Nota bene. The total linear momentum of an isolated, remember we've dealt with or term isolated system, remain constant in both magnitude and direction. And you cannot just leave things here. It's either true or nothing. The total linear momentum of an isolated system, that is number one. 2, remains constant in both magnitude and direction. There should be both magnitude and direction. So this is the principle of conservation of momentum. And this principle is going to allow you to calculate. But what does it mean? It says to us the sum of initial momentum is equal to the sum of final momentum. In other words, others they use it to say the momentum before is equal to momentum after, which is not correct if we are saying that, but we need to put the sum. The sum of momentum before is equal to the sum of momentum after, because we are going to deal with the sum. So if you're saying momentum before is equal to momentum after, it's not correct because we're dealing with the sum. So many times learners, they forget to write this. This sign means sum. So we are going to add all what is in before, then you equate to what is in after. So this is in symbol. And I want to say to you, use this symbol. It's very important that you are going to use this symbol. This, before you can start with calculation, your marks will lie here. That is your first mark. You write this because it's telling us as markers what you are saying. In other words, we have applied the law or the principle of conservation of linear momentum, or is letting us to be aware that we are going to apply the principle of linear momentum. So the sign, what does today mean? This one, it says the sum of all objects involved in the collision or explosion before. This is before collision or explosion. Remember, we said the sum. So this meant for a sum. Now, where is this sum? This sum is in initial momentum, in a state of starting. Initial means start. So it means you will be starting. So that is where you find your initial. So this one, it says the sum. Remember, don't forget this. The sum of all objects involved in a collision or explosion after the collision or explosion. And this one, it's a final momentum. So this side is initial, this side is the final. Hence, we denote it with I, this one with F. So it's very important that you deal with this. It's very important that you know what is this sign for. All right. Now, mathematical representation. Now, that sign, Pi equals to P2. Sorry, PV, not 2. It says, this is scientific, right? It's all scientific, right? It is the principle, right? Now, you want to formulate a formula that will assist us to calculate, right? We'll do it mathematical. That's why we're saying mathematical representation. So in mathematical, we are breaking this down. So we are saying momentum we are having two objects. Remember, I said we are dealing with two objects. So we are having object one. Object one, it has momentum. Momentum is what? Mass times velocity. So this is momentum. It's object one. This is object two. So it's a sum. Do you see? It means you are adding object one to object two. So the velocity of object one to object two. So this, we call it before anything happened, or it's at initial state. And then this one is object one at final velocity, and this one at final velocity, object two. We are still adding. So it shows you here that if you've got this, the sum of Pi, this is supposed to be the sum of Pf, in fact, sum of Pf, yes. Sum of Px, because F, because this is going to be final. So this side is a final, this side is before. So you must understand that. So we are going to use this formula, mathematical formula, to help us to calculate. Either it can be a mass, either the final velocity or initial velocity. It depends with the questions that has been asked, right? Or this formula, this one we call it's for calculating an elastic when they collide and separate or bounces off, right? They separate or bounces off, this one. But if it happened that they collide and move off together, right? What happened? We are going to use this one because before they collide or collided, what they do, they were separated. This one, they were separated. We've got one object having its own velocity, a momentum, and this one having its own momentum. But after collision, the two objects, they move off together. In other words, they are having, in fact, this formula is not correct. It was supposed to be V equals to M, V plus M, MI and MV, yes. This, all right? So in other words, they are going to move with one velocity, right? With one velocity, but their masses, they still maintain their masses, right? They will maintain their masses. So you will having, in other words, you must add the masses there. You must add their masses because they are moving, clinking together. They are moving the same, right? So we'll add the masses, the mass of this one and the mass of the other one, right? So what do we know now? All right, I want us to ignore this one and take this one to say, if two objects, this object is moving this way, and that object is approaching this one, and the two objects collide, this year there will be a collision, and these two objects move off together, right? Whether this side or that side. So, but they are moving off together, right? So, in other words, it tells us they are moving with a common final velocity. This is final V, because we don't know the final velocity, whether they are moving to the right or to the left. However, this object has its own mass and this one has its own mass. Then it means, therefore, if they are moving with a common velocity, then there should be one velocity that we need to calculate. And then we have the mass, right? Mass I, which is for the other object, and then the mass, let us say mass B mass A and mass B, because we are differentiating the object in terms of A. If this one is A, this one is B. This one will be A, this one will be B. You can say 1, 1, 1, 2, and 2, 1, 2, right? Because the mass will never change. So, in other words, then we are going to add the masses of this one, but they are going to move with a common velocity. So, it's one that we are going to calculate. So, it's supposed to be this one. You start with this one equals to that one. So, we'll cancel this one because it's not correct. All right. Now, it can be vice versa again. They will start combining, all right, and then they will separate. So, in other words, they will start with one mass, one velocity. They will move with one velocity, but they're still having separate masses, because if I carry this with me, then I've got my own mass, it has its own mass, but we're together. So we need to add. So in other words, in this one will be V M1, if it's 1, plus M2. All right. So equals to, then this is before. Before I was carrying this with me, right? We're together, moving with one velocity. And then I throw this away from me, then we separate. So it will be having its own velocity, and then I have my own velocity, but we'll be calculating which one, right? Which velocity we want to calculate. It's either this one or the other one. So it depends with the question. I think we understand in this regard, right? Now, this is a work example. Let us try to apply what we have learned. All right? And let's try to apply what we have learned. In application, question 1. A car of mass 1,500 gram is stationary. You see, as I'm reading, I'm underlining and I'm gathering. Now, what does it tell us? The car is at rest, ne? It means the car is at rest or stationary. Now, it tells you the initial velocity, VI, is equals to 0 because it's at rest. At a traffic light, it is hit from behind by minibus of mass. We're given the mass of the minibus, which is 2,000, traveling at the speed of 20 meters per second. Now we know this one, right? It's 20 meters per second. So this is initial velocity. All right? All right. Then, which is 20 meters per second. Right? Therefore, then they collide. Immediately after collision, the car moves forward. So this one hit this one at the back. It was stationary. But now, after they collide somewhere here, then this one move at 12 meters per second. We want what is the velocity of the minibus. That is what we need to calculate. All right. Now, first question says, state the principle of conservation of linear momentum in widths. All right. We know that linear momentum is, if you need to recall, it's a total of momentum before, there's a total sum of momentum before and the total sum of momentum after. But we don't define it like that, right? We define it last time, and they say it must be in an isolated system, and it must have both magnitude and the direction. That is, it's our definition, but we'll define it. But you know the definition as of now. Then we need to calculate the speed of the minibus immediately after collision. The speed of the minibus after collision is what we need to calculate. The driver of the minibus is not wearing a seatbelt. Remember, we spoke about this last. Describe the motion that the driver undergoes immediately after the collision. Remember, what is the purpose of the seatbelt? seat belt, right? It means we are linking what we have done last week with what we are doing today. And then state the law, right? State the law of physics which can be used to explain your answer about the motion of the car in 1.3. Right? These are the questions for this work example. We're given the scenario here. We understand the scenario. We must apply what we are given here. We've collected data for this one to use to answer this question. So number one, we are asked about the principle of conservation of linear momentum. So we are saying the total linear momentum in an isolated system is what I said in an isolated system remain constant in both magnitude and the direction. This is what we need to know. All right. Now, number 2 or 1.2. We need to do calculation. I'm just giving you a data here. Just as a data that we are going to use. We've collected the data. We know the car that was stationary, or the car, because we've got the car and a minibus, we can differentiate it with the car and the minibus. So the mass of the car were given as 1,500. Then the initial velocity of the car, because it was stationary, they said they stationary, then it's 0 meters per second. Then we were given the mass of the minibus, which is 2,000. And initially the car was traveling at 20 meters per second. Right. This is what we're given. This is before. This is initial state. Then they collide. After collision, the car move at 12 meters per second, and we want the velocity. That is what we are told to do, to calculate the velocity. Now, I said, when we start, learners, when we start doing this, we start with the principle. We apply the principle of conservation of linear momentum. Remember, we studied above. They've asked you, you got 2 marks for it, because this is 2 marks. You got the 2 marks. In the total linear momentum in an isolated system remains constant in both magnitude and the direction. But now, we need to apply that one. Then I said, when we come to this, we write total momentum, which is at initial, equal to total momentum final. This is what you write. This is where you're going to get the first mark. All right? Then you come to the mathematical. Remember the mathematical representation. You've got 2 objects. You've got the car and the minibus. So you say the mass of the car multiplied by the velocity of the car. Remember, this gives you momentum, right? This gives you momentum. This is momentum, right? Plus the mass of the minibus, multiplied by the velocity of the bus. These are initial, remember, these are initial velocity, all right? Now, equals to the mass. Now, what happened? They collide and then they move. They didn't separate. They didn't cling together. They just separated, right? So you cannot use the formula where they separate. You use it as they bounce off or they are separated. So now it means, therefore, this is going to be the mass of the car multiplied by the velocity of the car, of the car. This is final. Remember, this is initial. This is final, which is F. All right? Plus the mass of the bus multiplied by the velocity, the final velocity of the bus. All right? All right, this is the bus. All right? This is your formula that you are going to use is going to help you, but it does not have a mark. This one, remember, it's mathematics, and it's not there in a data sheet. So you already got the mark from here because this is scientific. So they won't award a mark there, but you need to know what does this say in terms of mathematics, because it's going to help you in terms of substituting. All right. Now we go to our data. What do we know? The mass of the car, they say, is 15,000. All right. The velocity of the car, it was stationary, multiplied by the initial velocity, in fact, 0. All right. Plus, because we've got this plus, remember, it's the sum, what we're talking about. Now, the mass of the minibus is 2,000, multiplied by, before, which was 20. Is it 20? Yes. It's moving at 20. That is initial. 20. All right. Equals to. Now, this is before. This is the side that everything started. That we have substituted. We have used this information. This is for before. We have used it as before. Then we go to after. What happened after? The mass doesn't change. The mass of the car still stays at 15,000. 1,500. Why I'm saying 15,000? It's 1,500. Sorry. It's 1,500. So, as it stays at 1,500, multiplied by. All right. Now, the car, it was head behind, and then it moves. All right. Then it moved at what? At 12, right, meters per second. So you've got a mass of the car, 1,500 multiplied by 0, plus the mass of the minibus, or of the minibus, is 2,000 multiplied by 20, equals to the mass of the car after collision stays the same, 1,500, equals to what? 12, right? This is the 12 that we are given, all right? Plus, all right? Now, what is the mass of the, stays the same, is 2,000, multiplied by, you don't know the velocity. Remember, we must get one unknown. So the one unknown, this is the one that you are going to calculate, the final velocity of the minibus after collision. That is what we need to calculate. Now, we go to our calculators. Now we start calculating. Now, what do we know? We know that any number multiplied by 0 is going to be 0, right? This is going to be 0. Plus, then we calculate, in our calculator, we say 2,000 multiplied by 20, that will give us 40,000, right, equals to, right? Then we have 1,500 multiplied by 12, right? Then it gives you 18,000 plus 2,000 VF, the one that we don't know, because if you multiply this, is going to be 2,000 VF. Then we want to remain with the unknown, right? We are going to take this one in the other opposite direction. Remember, they are moving in the same direction. In other words, they cannot change the direction. So in other words, it's going to be 4, because if you add this to this one, it remains as 40,000, right? And if you take this 18,000, the other side, what is going to happen? The sign is going to change. It's going to be minus, right? 18,000 equals to this one. All right. Then we can start doing our mathematics here. All right. We say let's say minus 14, 0, 0, 0. Then it gives us minus 20, it gives us, sorry, positive 22 equals to 2000. Right, F. But we want F, right? What do we do if we want F? We need to divide by both sides by 2000. This side we divide by the same amount. Then this one cancel out. What we remain with this side, we remain with F V equals 2. Let us divide. Then we divide by then it gives us 11 meters per second, right? In the same direction as the car. So they are moving in the same direction as the car because remember this one is what? It's a vector. It has a magnitude and the direction, and the magnitude is positive, what you get. So they are moving in the same direction. But the velocity that we have calculated for this one is 11 meters per second squared. That is how we are doing it. All right? All right? So this is how we've got our answers. And how do we apply the principle of linear momentum, the conservation of linear momentum. So let us see that we are right, because I've written on it, but here's the answer. Here's the answer. It's 11. All right? The answer is there. It's 11. So we have the answer. We already done. So we've got our answer. So we have proven that we've done the answer. So we've worked our answer. I wanted us to see as to how to apply this. First, what is very important is to deal with this. All right? That is your first mark. That is the equation that you're going to do. Then you substitute. As I've done my substitution, I've done it correctly. All right? This is our substituting. So this is the mass. This is the initial velocity. This is the mass. This is the initial velocity. This is the mass after collision. Then the final velocity that you are given, the mass and the final velocity that we want to calculate. And then you do it around, with a mathematical instrument, which is the calculator. You calculate whatever that they want you to calculate. At the end, you will find your answer. This is your answer as we did it. Right. Right. Now, the question was, let us go back a bit for that question quickly. The question was saying the driver of the minibus is not wearing a seatbelt. Describe the motion of the driver undergoes immediately after the collision. Now, this is what we have. The driver will continue in a straight uniform. The driver will continue moving forward at the same velocity as the minibus until the driver strikes the headboard or the windscreen. In other words, you know Newton's first law. We spoke about it. We'll continue with the same motion of the car. Remember, if you are sitting on the car and the car is traveling at 120 meters per second or kilometers per hour, it means as a passenger or a driver, you are traveling with the same speed of the car. So the driver will be traveling with the same velocity as of a car, and then the driver will hit the dashboard or will hit the windscreen if you are not wearing the seatbelt. So it's very important. Remember, we spoke about it, that you need to wear the seatbelt because it prevents injuries. So it will prevent injuries. So you need to wear the seatbelt. Now, they say which law. They can say which law and state the law, right? Remember, it's Newton's first law, all right? And then it can the law of inertia, because it deals with inertia as well. So the Newton first law says that a body will remain at rest or move in a constant velocity unless the non-zero resultant force act on an object. So this is the Newton first law. So it means your answer applies to what? Newton first law. That is what they wanted you to give. So learners, it's very important that you adhere. These are very simple marks. This is where you get your 2-3 marks. You see, just explaining, because here is an application of a law, and this law, it applies. The law that we did in forces, it comes in here, and you must know them, right? This is another work example 2. So you've got two objects attached to in a string. This can be an explosive one, because they are at the same position when they begin before, and then they will explode to move separately. Now it says a diagram below shows a trolley P and Q, held together by means of a compressed spring on a flat, frictionless horizontal track. The masses of P and Q are 400 gram and 600 gram respectively. So you've got the masses. Now, what do we need to take into cognizance here are the SI unit. We never calculate with grams. Always you calculate with kilograms. So in other words, what comes to your mind is that you need to do conversion here. So conversions is very important. You need to do what? Conversion here. So grade 10 work, when we start, we did what? Conversion of SI units. So this, you cannot use it as 400 gram. You use it as a kilogram. But how do you convert this into kilogram, by the way? Yes, kilo means 1,000. In other words, you must divide this one by what? 1,000. And divide this one with what? 1,000. Because that is right? So you divide all the time. You divide by what? 1,000, right? If you divide by 1,000, so we are converted to what? Kilogram, right? We use kilogram, not grams. Grams, as stated there. Now they say when the trolleys are released, it takes 0.3 seconds for the spring to unwind to its natural length. Now, trolley Q then moves to the right at this speed, 4 meters per second. So we are told. So it's only this Q that will move to the right, right? It moved to the right with a speed of 4 meters per second. In other words, we don't know what is the speed of this one as they separate, right? Now, state the principle of conservation of linear momentum in weights. Always the question will be there, which is 2 marks. A question will be there, learners, 2 marks. So we need to know the principle, right? Then calculate the velocity of P after the trolley are released. Calculate the velocity of trolley P. Now we want the velocity, this one, after they are released, right? That is what we need to calculate. And then they say the magnitude of the average force. Now, I said it last week to say, once you have time, you must have in mind that you will be asked for a force, to calculate a force. Once you have time, bear in mind that you will be asked to calculate for the force. And we did it last week, how to do it, but we are also going to do it. So, but I'm cautioning you, once you read the statement, and the statement says to you, the time was used there, expect a question that you will be calculating a force, or vice versa. Once you're given a force that is being used, expect that they will want you to calculate what? Time. It's very important. Right. So guard against those questions. Once you have time or a force, giving one or either, they'll want you to calculate either one. Right. Now, the principle, you must state it. Then if you state the principle, the linear momentum of an isolated system remain constant in both magnitude and the direction. That is the principle, which is 2 marks, right? This 2 or nothing, I still remain. This 2 or nothing. Know the principle, learners. Know how to state the principle, all right? Now, I've gathered the data for us that is going to be used to calculate the velocity of P. Right. What does it say? We've got the trolley P with the mass of 400 gram. Then we have converted the 400 gram. Now, quickly, let us convert it. I've done it, but let us do it for all of us so that we are sure we've done the correct one. It's 400 divided by 1,000, right? Then it gives us 0.4. Always we divide by 1,000 because kilos means 1,000, right? So we convert this one, the 600 gram. We divide by what? The 1,000, 600. Come on. 600 divided by 1,000, then it gives us what? 0.6. 0.6. Then I've combined. You are no longer going to use these ones. We use these ones because they are in gram, right? So they are in gram. So it's very imperative that we use this one, right? So what is going to happen? We have the mass now. We have converted the mass. When we start, initially, they are at rest, both of them. Both of them, they are at rest, no motion. So in other words, the velocity, the initial velocity of trolley P, it's 0, and trolley Q, it's 0. So they've got 0 initial velocity, both of them. And then the force was applied, then they move off together. Then the other one we're told, which is Q, is moving at 4 meters per second. And the other one, we don't know the velocity. We need to calculate the velocity. Now, where do we start? All right? I'm not going to do it. I've done it already, but I want just to show you that we start from here. Let me just write here. We start from here. Right. This is what we start. This is where we start. This is where we start. This is very important. This, learners, is very important. This one. It's your 1 mark. Then from there, you can go to your mathematical equation or mathematical representation of a formula that we use. The one that of a sum, sum of momentum initial, sum of momentum final, which is mv q mv plus mvp, right, equals to mv, right, But here, because they were linked together, I will say to you, we'll use a common velocity, adding the mass. All right? And then you calculate the other side. Right? Now, let us look at how I do it. We take the positive motion, as the right is positive, right? Then we've got the mass of this one, which is 0.4, multiplied by 0, which is there at rest, plus you've got the mass of the Q, which is 0.6 multiplied by 0.4, and then we've got equals to. Now that is where we need to calculate, right? This is 0.4 multiplied by Q, because we are told that we need to calculate this one, right? Which is the P, right? The P1. We are calculating the P1. So this is the velocity that we calculate for the P. But this one, after they separate, it moves at what? At this one, right? So they move, they move at with the speed of 4 meters per second, because we are given 0.6 as a mass, right? Now, this side, if you multiply this by this, you'll get this one, because you have this one. You multiply this by this one, you have this one, right? This side, this is 0, remember the mass that you are given there. This is the mass that you are given. This is the mass, and this is the velocity. This is the velocity. This is the mass, this is the mass that you are given. This is the mass. This is the velocity. This should be 0 there, right? So this side, what we've got 0, all right? Then after, we want what? We want the unknown, right? The unknown is this one, all right? We transpose 0.4 V. This is 0.4 V. If we transpose it the other side, it's going to give us a minus, all right? Equals 2, all right? If we multiply the 2, it gives us 2.4, all right? This is 2.4. So we are leaving 2.4 the other side, because these are not the same numbers, all right? Now, we want, what do we want now? We want V to remain. We'll divide by 0.4. We divide, you can say we divide by minus 0.4. We divide by minus 0.4. All right? Then if you divide the two, let us see, this will cancel each other. This one will remain with what? With this V that we are looking for. Now, if we go to our calculator, we say 2.4 divide by 0.4. Then what does it give us? It gives us 6. But it's minus 6, remember, because we divided by minus. It gives us minus 6. All right? Then, what does it tell you? It tells you that this one will be moving in the left direction, right? Because of this minus. So it moves in a left direction. So we are apologizing for these glitches of errors. So this side is supposed to be 0, 0, because the two were just stationary, right? So we have 0, 0, then we've got 0, then we take this one that we want on the left hand side, then the sign changes when you go on the left hand side. The sign will change. Then it's going to be negative, and then you do your calculation, then you get your 6. That is how we have calculated, right? Now, calculating the force, all right? Remember this formula. Remember this formula, right? This formula is for impulse. Do we remember? Now it has a net force multiplied by change in time equals to change in momentum. Now you can calculate the time, because you can calculate the time, you can calculate the force, because we'll be giving either. But in this time, we're given what? The time. So we need to calculate what? A force. So we can calculate the force, this one. We have the time, we have the change in momentum, right? Or we can calculate the change in momentum. So how do we do change in momentum? We know this is the formula to calculate for change in momentum. Now, the time we are given is 0.3. This is the time given. Then equals to, now which object they say we need to calculate. Let us go back a bit faster. They say Q, right? So in other words, we are going to deal with Q, all right? With only Q. So the mass of Q is 0.6. Now we know that Q traveled at 4. The velocity was 4 then, right? Then the initial was 0. So now if you multiply this one, it's going to give you, all right, let us do it. 4 plus 0, it's 4. Then you have 0.6 multiplied by 4. Then it gives you 2.4, right? We've got 2.4. Then we are going to divide by 0.3 this side. In this side we've got 2.4, right? Then this one will cancel this one. We remain with this one. Then we say 2.4 divided by 0.3. Then it gives you 8. It gives you 8. That is the force that they want you to calculate, right? That is the force. So what helps you is what is the time given, because we have been given time, all right? So we have calculated that one. Now, this is what I want you to know, because what are coming are just questions. We're dealing with questions. But I put this slide so that you must know this. You must know it. The difference between the elastic collision and inelastic collision. This is very important. So take this and paste it and look at it over and over again. Momentum before collision is equals to momentum after collision, right? That is, even this side is the same if we take the principle of conservation of momentum, right? This is the formula for principle of conservation of momentum in both inelastic and elastic. Now, we said, and I still say, there are two things that you need to, that need to come to your mind when it comes to elastic collisions, right? The total kinetic energy, right, before collision is equals to the total the kinetic energy. So in other words, you will be having you will be asked to calculate the total kinetic energy before collision is equals to the total kinetic energy after collision. So in this one, they are equal. All right. So the total kinetic energy in joules, because energy is in joule, now before collision is equals to the total kinetic energy after the collision. And you'll be required to calculate that. All right. You will be required. So this is what it says. This is before, this is after. They are equal when we are dealing with elastic collision. But when we deal with inelastic collision, the total kinetic energy in joules before is not equals to the total kinetic energy after collision. That is the difference that we need to know. This is inelastic, this is elastic. So this is not equal. There are two, they are not equal, before and after. But this one in an elastic, they are equal. All right? Then you will be asked to prove that in terms of calculations. So it's very important that you know that. So this slide, I will advise you to keep it, and especially know this, because it is guiding you as you are going to move on with the calculations. Now, this is the work example that I want to move it fast. We've got two balls, ball number 1 and ball number 2, right? These are a bill ball. Then we were given a mass of the grams. Remember, once you look at grams and you come across grams, it means you must do conversion. That must come to your mind, right? We are given a mass of ball 1 as 150 gram, collide head on as shown in a diagram below. Ball 1, they say each mass has this. It means both masses, they are having the same, because each mass or each ball have the mass of this, each ball. So they're having a mass of this, right? Ball 1 was traveling at the speed of 2 meters per second, and then ball 2 at the speed of 5 meters per second. After the collision, ball 1 travels away from ball 2 at this. So ball 1 is the one that travels after the collision. So this is the picture that we are given. These two balls are approaching one another, traveling with 2 meters per second, the other one 1.5 meters per second, approaching one another, and then having the same masses, right? And then the other one collides. After collision, the other one, which is ball 1, move away from ball 2 at the speed of 1.5 meters per second, and we want the velocity of this one, right? Okay, this is very interesting, but it is what we have done. So they say calculate the velocity of ball 2, after collision. Now, first what come to mind, you convert this one, right? You know the conversion. Now we calculate. Then they say prove that the collision was elastic. Show by means of calculation. To prove, you show by calculation. You prove, you show by calculations, right? So they say you must prove. Remember this as you are going to prove, right? Let us move fast. Then this is what we have. We start by this all the time. We said it. That is where we start. Don't lose it. Don't lose it, please. We start there as we calculate. This is where your 1 mark lies. And then you convert this into mathematical, right? Then you substitute. Remember, we are going to convert our mass. Our mass given was 150 gram. And then if we convert 150 gram, we say 150 divide by 1,000. Then it gives us 0.15, which is what we have here. Okay, so we have this. This is what we have. Then it's 0.15 multiplied by 2. Remember, we're given the other one was, the first one was moving with 2 meters per second plus the same mass, 0.15. Right, now the direction, because remember when we go here, if we go here, they are approaching each other. This one is going to be in a direction east, positive. This one in a direction this side, which is west, negative. So it's going to be the other one negative, the other one positive, because they are approaching one another. So take this position east as positive, right? Take east as positive, then west will be negative, right? Right. Let us go again. All right. So hence we put minus here. The minus is a direction. Remember, velocity is a vector. So we put minus. So that minus represents the direction, west. All right. Now we've got this one. After collision, this is before collision. This is the mass. Then after collision, we're told that it changes direction, right? So we put minus because it went west. So it changes direction. So remember, our west is minus. So it's going to be 1.5. All right? 1.5 west. That's why we put a minus there. Then plus the mass of the second object or second ball is 0.15. The velocity that we don't know. Then you do your mathematics. Then this is our mathematics calculations. You use a calculator. You multiply this by that. It gives you that. You multiply this by that. It gives you that one. Then same again. You do it that side. You multiply by this by that. It gives you that one. Then you want V. Now, what you do, you take all the numbers together. You group them together. It means you are going to transpose this one, this side. And the sign is going to change, right? Then this side you are going to remain with this one because it's the one that we want. Then if you group all your numbers, because this one is positive, you start here, this subtract this one, adding to this one because it's going to be a positive when it comes this side. Then it's going to give you, right, take this one, let us say you start dealing with this one, then it gives you this one, you transpose this one, it becomes positive, then equals to the one that remains. All right, then you divide by whatever that you get the other side, this side, you are going to divide it here. Your answer that if you say this plus this, 0.075 plus 0.225, then you add it together. We are going to divide it here. Then after the division, you'll get your answer as 2 meters per second. That's what they want. But what is the direction? The direction, because it's positive, is going to the right. Remember, positive going to the right or going to east. So that is positive. So you don't leave your answer here. This is still mathematics. Then you put it in scientific term, which is, this is scientific, right? So this is how we got it. But what I want to emphasize is the conversion. Conversion is very important. Once you use grams, everything is wrong, right, learners? Right. This is all right. This is the solution for kinetic. They want us to prove. Now, how do you prove? Equal the sum of kinetic initial is equals to the sum of kinetic energy, total kinetic energy final, right? We want to prove this, that they are equal. Now, I want to emphasize this. You don't do calculation equating them. You are going to be given a wrong mark, or you are going to be wrong. What you need to do, you separate them. You do them step by step. You start with before, and then you come with after. This is before. Then we know that kinetic energy, what's the formula for kinetic energy? Is half mv squared. That is the formula for EK. This is the formula for EK, right? So we take the kinetic, the formula for EK. This is one. This is before, is the sum of the two. So we substitute. We know that half is 0.5 multiplied by 0, this is the mass that we have. Then we're giving this one before. Then plus, then the other object, it was this before, and the mass stays the same. The mass, yes, stays the same. Then the moment, the velocity is this one, and then so this is the half, this is the mass, and then this is the velocity. But what is very important that I must tell you, guys, you must not forget the squares, these squares. Once you forget that, your answer will be wrong. The squares, remember the square there is very important because it means the number in the bracket must multiply itself twice, right? Then you start calculating. You do your calculation. 2 times 2 is 4. 4 multiplied by 0,15 multiplied by 0,5. Then you get your answer as 0,3. Then you come to this one, 0,5 multiplied by 0,15 multiplied by negative 1,5 squared. Then you get your answer as this one. Then you multiply the 2, then you have your, you add the 2, then you have your answer as this one. That is before, right? Then you go to after, then after collision. Remember, I said you do it separately. You don't equate them as this one says. But you do this one first. This is the calculation for this one. Then you do the other one, right? Now, you do the same formula. You do the same substitution, right? But now the substitution, you go with your direction. Remember, we have calculated the after velocity. Now you've got the after final velocity. It means you have two velocities, right? Now you've got 0,5 multiplied by 0,15 multiplied by negative 0,15 squared. That squared is still there. E plus 0,15 multiplied by 0,5 multiplied by 0,15 multiplied by 2, right? This is what you have, right? Then you multiply the 2, you got this one, you multiply this one, you get this one. Then you add the 2, it gives you the same answer as that one. What does this tell you? This tells you that the momentum, the sum of the kinetic momentum before is equals to the sum of total kinetic momentum after it's equal. So they are equal. So the answer, because the answer are the same, it means this is equal. And this, therefore, it tells you this is what? An elastic collision. Remember, once the answer are equals, because they want it, they are equal, then it tells you that this is elastic collision. Is what they wanted you to prove, that this is elastic collision. So this is an elastic collision because the answers are equal. You say, therefore, the sum of kinetic energy, total kinetic energy before is equals to the sum of kinetic energy after, then this is unequal. But if the answers were not equal, we're going to use this sign. This sign means they are not equal. If the answers were different, but in this regard, the answers are the same, then we have proven, then you get your marks. So this is how we are going to deal with this one. So these are the questions that I want you to do at home. They give you knowledge. You test yourself all the time. You just take, then you try to test yourself. These are the structures questions. These are from the exam. They are doing the same as we are going to, we did. This, they want the principle of the linear conservation, the principle of conservation of linear momentum, in which calculate the speed in the system, and then by means of calculation show that is elastic or inelastic, is what we have done. Explain the airbag, what you have done. So the same thing, they keep on doing the same thing. Now this one, define momentum. This one, principle of conservation of momentum, you state it. Calculate. So these are combined. They say combine the V. When they are combined, then it's easy. And then you explain the airbag. They keep on one and the same questions. So these are from Eastern Cape, September questions. So these are the questions I've gathered from the question paper. This is the Free State. Same thing. They give you a scenario here. Then they want you to, which conservation principle can we use to calculate the velocity of the wreck after the collision? You know, they want the principle. You know that. Then write down the principle. So it's a principle of conservation of momentum. Then what? The principle. Then you state the principle, which is 2 marks. They calculate. So it's one and the same thing. One and the same thing. So these are the questions that I want you to deal with at home. Then you'll deal with these questions, and then you'll find your essence, what does they mean? So they do one and the same thing. If you can do these questions and practice with them, I'm telling you, you are done with momentum. From where we started and up to this one, we are done with momentum. So learners, in conclusion, because we have run out of time, I want to say this to you. You do these questions and then you practice, make perfect. The last motivation word, it says, this picture teaches us one important lesson. Today you are flying up the sky. Tomorrow you will need someone on the ground to carry you up. So be humble, love people, and invest in people. Don't underestimate people below you. Carry them above if you can, but don't push them down. Thank you, learners, for these lessons. For today, it's end. I hope you have benefited and you are going to pass this topic. Thank you for watching this program. Please remember to sanitize, wear your mask, maintain social distance, and keep safe. Thank you so much, learners. I wish you good luck.